Welcome to The Explainer. Today, we're going to crack open the engine of the digital world and see what actually makes it run. We're going to break down programming into its most basic parts. You know, the simple logic that powers pretty much everything, from your phone to your car. So, let's get started.
It's a pretty cool thought, isn't it? And while it sounds super complex, when you get right down to it, programming is really just a way to communicate. It's all about giving a machine a set of really clear, really specific instructions to get a job done.
And the language we use for this is called code. Honestly, the best way to think about it is like a recipe. Seriously, each line of code is just a step, and if you follow those steps in the right order, you get the result you want, whether that's a perfect chocolate cake or a working app.
So, where do we even begin? Well, with our very first word. The most basic building block of any program is just a simple command, a single instruction that tells the computer to do one specific thing.
In a ton of programming languages, that first word is print. Its job is incredibly simple, but also really powerful. It just tells the computer to display something on the screen. This is our fundamental way of getting feedback and actually seeing what our instructions are doing.
And here it is in action, the classic hello world. There's a reason this is the first thing every new coder learns. With just one simple line of code that says, "Hey computer, print out hello world," the computer does exactly that. It's the perfect, most basic example of cause and effect in the coding world.
Okay, so making a computer talk is cool, but what about making it think? Well, the next building block we're going to look at gives our programs a kind of brain, letting them make choices based on whatever is going on.
So how do we do that? We use something called an if-else statement. Think of it like a fork in the road for your program. We're basically telling the computer, if this one thing is true, go down this path. Else, if it's not true, go down the other path. In this case, we're just checking if a number is even or odd. It's a simple choice.
And you can see exactly how that fork in the road works here. When the program gets the number 6, it follows the if path and tells us, yep, that's an even number. But when we give it a 5, it takes the else path instead. See? The program isn't just blindly following steps anymore. It's actually making a decision based on the rules we gave it.
Right. So our code can give commands, and it can make decisions. But the real superpower of computers, the thing they do better than anything, is doing stuff over and over and over again without ever getting tired or bored. This is where our next building block, the loop, comes in.
I mean, just imagine you needed to print the numbers from 1 to 100. Are you going to write 100 different print commands? No way. That would be a total nightmare. It's slow, it's messy. There's got to be a smarter way to do it. And there is. It's called a loop. A loop is basically your own little automation machine. The logic is simple. You give it a starting point, a condition to check for, and an instruction to follow. The computer then does the instruction, checks the condition again, and just keeps repeating that whole process until it's told to stop.
And the result is just pure efficiency. Instead of writing 10 separate lines of code to print 10 numbers, a loop does it in just a few. It handles all that boring, repetitive counting stuff for you. This is exactly how programmers get computers to do all the heavy lifting.
And what's really cool is that you can use that same simple idea of repetition for some surprisingly creative results. This triangle pattern, for example. It might look complicated, but it's really just one loop running inside of another one. It's something programmers call a nested loop. One loop handles the rows, and the other one tells the computer how many stars to print on each line. Simple blocks, but a pretty complex-looking pattern.
Okay, so we've got our key tools, commands, decisions, and loops. But what happens when our programs start getting bigger and more complex? Well, things can get really messy, really fast. And that brings us to our next crucial building block, organization.
So let's say you have a task you need to do a bunch of times in different parts of your program, like, I don't know, reversing a word. Are you just going to copy and paste the same logic over and over again? Because that would be a total nightmare to manage if you ever needed to change it. This is where something called a method comes to the rescue. It's also called a function. It's basically a block of code that does one specific thing, and you give it a name. Think of it like creating a specialized tool for your toolbox,
Once you've built it, you can just grab it and use it whenever you need it simply by calling its name.
And this right here is a perfect example. Somebody wrote the logic to reverse a word one time and then packaged it up into this handy, reusable method. So now, anytime they need to reverse a string like programming is fun, they just call that one method. They never have to think about how to reverse a word ever again. It just works.
All right, now for the really cool part. Let's see how these 4 fundamental building blocks, our commands, decisions, loops, and methods, all come together to create programs that can solve some pretty interesting puzzles.
You know, this quote from our source material really hits the nail on the head. It's saying that even programs that look super complicated on the outside are, at their core, built from the exact same basic fundamentals we've just been talking about.
Take this, for instance, checking for something called an Armstrong number. Now what's that? It's a number that's equal to the sum of its own digits, each raised to a certain power. It sounds complicated, right? But just look at how the program actually figures it out. It's just using a loop to break the number apart and do some math. Then it uses a simple if-else decision to check if the final result matches the original number. That's it. It's all just loops and decisions.
And it is the exact same pattern here for checking if a word is a palindrome. You know, a word that reads the same forwards and backwards, like madam or race car. How does the code figure this out? It's not magic. It just uses a loop to create a backwards version of the word, and then an if-else block to see if the original and the reversed versions are the same. Simple blocks, powerful result.
So, here's the biggest takeaway from all of this. No matter how complex a piece of software seems, whether it's a simple little app or a giant, sprawling video game, it is all built from these same core ideas. Commands to do stuff, decisions to make choices, repetition to save work, and organization to keep it all sane. These are the bricks that build our entire digital world.
So, you've now seen the fundamental logic that drives so much of modern life. These are basically the Lego bricks of the digital age. The only real question left is, what will you build with them?